All right. So today we're continuing our discussion of digital logic operators. Last class, at the end, I put up a couple of binary operators. Binary operators meaning that there are two inputs to this function. So we call them A and B. They could have been any letter. And we went through all the possible combinations of two binary variables. First combination 0, 0, second combination 0, 1. So that covers, while A is 0, B can be either 0 or 1. If A is 1, B can be either 0 or it can be 1. And then we went through three operators: the AND operator, the OR operator, and the NOT operator. Now, AND is really A ANDed with B, OR is A or B. NOT is a unary operator, meaning it only takes one argument. So in this case, I'll say NOT A. We can also look at NOT B, but it's the same operator. Okay. And here's how we define these logical operators. AND is true if and only if both inputs are true. Okay, another way of thinking about the AND function is false if any input is false. So true if and only if both inputs are true. That's, in this instance right here, A and B are both true, so the output is true. The rest are false. If you look at it the other way, from the flip side of the coin, it's false if any input is false. So here, these first three lines have a 0. They're false in at least one of the input operands. So that's how we define the AND function. OR is a function that we define to be true if any inputs are true. We can also think of it as false if both inputs are false. So, or if both inputs are false, only occurs in this first line. So it's false. It's true if any of the inputs are true. So in this case, it's like that. So it almost looks like it's upside down and inverted from AND. Now NOT, and I'll try to fit this in here, NOT invert the input. All right. If the input is a 0, the output will be a 1. If the input is a 1, the output will be a 0. So in the case of NOT A, all we have to do is look at the A column and invert it. So instead of 0, 0, 1, 1, it'll be 1, 1, 0, 0, the exact opposite of A. NOT B is still the same thing. It's the exact opposite of B. 1, 0, 1, 0. Questions so far? These are the definitions of these three operands. And these are the basic operands of Boolean algebra. Now we can represent these functions in a couple of different ways. We can represent them algebraically. We can represent them graphically. Oops, undo. Algebraic, graphic, as a timing diagram. We can represent them as a truth table. Now, we've already done the truth table. That's what this previous setup is. Truth tables have the inputs on the left, all possible combinations on the left, and then the outputs. Algebraically, we use symbols that we're familiar with. For and, we use the multiplication or the dot symbol. So A dot B is A and B. Sometimes, just like in multiplication, we do implicit multiplication. AB without the dot still means A and B. For OR, we make use of the plus symbol. A plus B. In this course, always, we're using that to indicate A or B. And there is no shorthand for that. For not, we have two ways, or actually three ways of recognizing not. First is to say A prime. Another way is to say exclamation point A. Actually, there's quite a few now that I'm thinking of it. Also, we could say tilde A. For the most part in this course, I'm going to use A with an overbar. Okay, this one is our preferred symbol. A with an overbar would be read as not A, or A not, depending on how you're reading it. But it's the inverse of A. So that's algebraic for and, or, and not. Graphically, and, or, and not use some graphical symbols. And is represented by a D. Okay, or is represented by that sort of Starfleet insignia symbol, and not is a triangle with the circle on the end of it, or a party hat turned on its side. Depending on the number of inputs, a 2 input might look like that, and always has only one output. In fact, all of these functions always have a single output, but they can have multiple inputs. So and has 2 inputs in this case. This is a 3 input OR. Not is the only one that's a unary operator. It is always 1 input. Okay, we could have as many as we wanted. We could have 5 inputs here. Most of the time, we treat these as binary operators. So we start with just 2 inputs at a time. You can always expand these out to more inputs, and we'll talk about that. So we've done algebraic, we've done graphic, we've done a truth table on the previous page. Timing diagram is just a slightly different way of representing things. And I want to get into timing diagrams for a second here. Timing diagrams are graphs. They have a y-axis and an x-axis. The x-axis usually represents time, whereas the y-axis isn't so much Cartesian as it is a representation of multiple values. So here I'll have a, b, and y, and I'm going to represent the and function on this. So over time, we're going to vary the a, the b, the a and the b symbols. Now, each of these is actually going to have its own sort of swimming lane here, if you can picture that. Now, when I start, I'm going to start with A towards the bottom of its swimming lane. There are 2 values that it can take on. It can take on 0 or 1, as can B, 0 or 1, and Y can take on 0 or 1. Those are the values. This timing diagram is going to show us graphically what's going to happen over time. So what I'm going to do is I'm going to start, and I'm going to start with A low for 2 periods. Then A is going to go high for 2 periods. And that's just, periods are just time units. This could be a second, it could be a millisecond, it's not really relevant. And then I'm going to have B low, and it'll go high after a single period. Then it'll go low after a period. And then it'll go high again. Now, what I've come up with here is a timing diagram where A is 0, and then it's 1. So it's 0 for 2 timing periods, and 1 for 2 timing periods. B goes 0, 1, 0, 1. So if it's high, it's a 1. If it's lower, it's a 0. And now I need to relate A and B to the output. A ANDed with B. Now the rule for AND is it is true if and only if both inputs are true. And that occurs right here, when they're both 1. In all the rest of those instances, it's 0. This is what you're going to see today in lab. You're going to see a lot of timing diagrams on the logic analyzer, and this is what you would expect to see. Now, on your logic analyzer, since you're going to be generating this pattern multiple times, you're actually going to see it go 0, 1, 2, 3, and then repeat. They're going to go 0, 1, 2, oops, hold on, undo. 0 and 1. I have to get this right here. All right, you'll see it repeat, and you'll see this also repeat. So this is one whole, how do I want to say that? One whole cycle. It's gone through all the possible input combinations. But your logic analyzer and your word generator are going to go through this multiple times. So you only need to zoom in lab on one cycle, and you'll be able to see that you've got a 0, 0, 0, 1. Now this is actually extremely close to our truth table representation. If you were to take this and flip it 45 degrees down, what you'd see is 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1. And if I go back over here, you see 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 0. That's the whole thing. Truth table and timing diagram are two ways of representing the same thing. This is just as an experiment over time. I could redo this for OR and for NOT, but I think seems pretty straightforward, right? Timing diagram is just, I actually like I never have explained it as swimming lanes before, but I kind of like that description. You have 3 lanes of data, and you can either be on the lower part of the lane or the upper part of the lane. One of the things I want people to be aware of is you should really respect your swimming lanes. I know in the past I have seen people who started off low and then went high, and then they went higher, and then low, and then they went higher twice. That is not a timing diagram. If you have things that are crossing over your lanes, you have a big problem. Also, try and avoid starting high and then going higher and then going low. There's only 2 values that you can have, either high or low. Okay. So when it comes to representing functions, new page, functions can consist of these operators used in any combination. So here is a function f, which is or takes in arguments of x, y, and z, just like you would see in regular algebra. Each of these, however, is Boolean, or are Boolean variables. They can only take on 0 or 1 as input arguments. So that's a function of x, y, and z, and that function is x or y and z. That's how you read it. X or y and z. And there are a few things we need to talk about before we start to try and analyze this. because in Boolean algebra, we do have an order of operations. Okay, the order of operations, first, anything in parentheses, with an E, parentheses. Second is any not function. Third is any and function. And fourth, any or function. If you try to evaluate an or function before evaluating all and functions, you're going to get the wrong answer. Just like if you tried to do addition before multiplication in a long, complex sequence, it would be a problem. So I have here two operators, or and. So the question I have for you, x or y and z, x or y and z. I have explicitly put parentheses around these arguments. Which one of these is equivalent to that without parentheses? In other words, which one do I do first based on this order of operations? The top or the bottom?
The bottom.
The bottom is correct. This is wrong. To do the or before the and is incorrect. So there is an implied set of parentheses around that and. So we can represent this function in a couple of different ways. Let's start with a truth table. Again, f equals x or yz. Actually, I didn't copy that down correctly. Okay. There should be a not over the y. I missed it when I was copying. But that lets us use all three functions. So that'll be not y. And again, not happens before and. So you'll do not y, then the result of not y anded with z, and then the result of that and operation with x, ORing it with x. So there is my algebraic representation of this function. I can also represent it with a truth table. All I have to do is list x, y, and z. And I have to list all the combinations. Sanity check here. I have three variables. Each of them can be 0 or 1. How many combinations will I have? 2 to the third is the correct answer. And what is 2 to the third? Count it off on your fingers if you can't. It's 8. 2, 4, 8. And the shortcut to doing this is since there's 8 total, we start by splitting it in half. 4 zeros, 4 ones. 2 zeros, 2 ones. And then finally every other. Okay? And in this case, it's actually going to be easier, rather than just having one output, I'm going to do it a piece at a time. So first, I'm going to find out what not y is. Then I'm going to figure out what not y and z is. And finally, I'll figure out what x or not y, z is. And that'll be the full equation. But each time, I'm going to be looking at it as a group. So not y is actually pretty easy to figure out. All you have to do is look at the y column and flip it. So here where it's 2 zeros, 2 ones, it'll actually be 2 ones, 2 zeros, 2 ones, 2 zeros. So the y column directly created that column. Now this next sub answer is not y anded with z. And, as a reminder, has a truth table like that. Only if both of them are 1 will the output be 1. So the truth is, any place that there's a 0, my output will be 0. So I'm going to look at this right now and say, hey, I've got zeros in y bar, right? So if there's a 0 in y bar, there definitely can't be a 1 in the and quotient there. So then I can also look at z, because I'm taking z ANDed with y bar, and any place there's a 0 in z, I'll put a 0. And now there's already a 0 in this column, so the fact that there's 2 zeros doesn't change anything. So the last z, okay, there. Everything that remains now, if I look, z and y bar, they're both 1. And as we see, that's a 1. So there are lots of different ways to fill out a truth table by analysis. So finally, to label this, that column and that column combined to make my output column. The last thing I'm going to do, and I'll do it in black ink, x combined with this column will give me a result. So OR says, and I'll come over here and do OR, AB OR 0, 0, 0, 1, 1, 0, 1, 1. OR is true as long as at least one of the output or one of the inputs is true. So in this column, any place I see a 1, I know that I will have a 1 on the output. And then I look at x, any place x is 1, I will have a 1 in the output. Again, the fact that there was already a 1 here doesn't change that fact. Everything that's left, if I look, is 2 zeros. 2 zeros does give me a false. So my final truth table is actually this. That and the inputs together. These are intermediate truth tables. Okay, this is our truth table. 0, 1, 0, 0, 1, 1, 1, 1. We would also call that F. Question?
You don't make a X or Y not section just because they don't go together?
Yeah, you would never do that because you don't actually evaluate X or Y naught. You evaluate X or the quantity Y naught and Z. Okay, there's that built-in parenthesis there. So that's a truth table representation. If we were to represent this graphically, I need a new page. There we go. F equals X or Y bar Z. We're going to take, and we have to pay attention to our order of operations. So I've got over here X and Y and Z. Now, I'm going to AND together Y and Z, but I'm really not doing Y, I'm doing Y naught. So I've got to invert Y first, and then I can AND those two things together. Finally, I OR the result of this AND gate with X. So there's my OR gate, my graphical OR gate. And the output of that will be F. Let's make that a little bit cleaner. F. That's a graphical representation. We are showing that we have to invert Y first, then AND it together with Z. Then we OR X with that result. Graphical representation. Now, when you're building circuits in the future, this is where you're going to start. You're going to come up with some kind of an equation. Then you're going to have to draw it graphically. Then you're going to have an implementation schematic where you understand that this is a 7404, and that'll be pin 1, and that's pin 2. You'll look this up. You won't just know this off the top of your head. This is a 7408, and that'll be pin 1, that'll be pin 2, that'll be pin 3. This will be a 7432, pin 1, pin 2, pin 3. So then you'll know that you'll have to connect pin 3 of the 7408 chip to pin 2 of the 7432 chip. You're actually going to be using each of these chips in lab today. Okay? And so you'll see that the truth table actually holds out for this because you're going to be generating timing diagrams for each one of these functional gates. If I didn't explicitly mention this, we call each of these a gate, a logical gate. Now, As a rule, we will typically simplify things algebraically when possible. And there are rules that help us simplify long and complicated expressions down to much simpler expressions. The simpler the expression, the less hardware we need to implement it, which means it's going to take less time to implement and it's going to cost less money. And as an engineer, we always want to do things for the minimum price point and still get functioning results. So let's go over some rules here. And these algebraic rules operate on one or more Boolean variables to simplify things. Typically, we do have an OR version of them and an AND version of them. And they do have a name. All right, so this is going to be a big table. So the first thing we have to look at is some Boolean variable ORed with 0. And let's reserve a little space down here. A, B, OR, and. This is just as reference so you can see it. Okay. And what I want to call your attention to is if you split this here, you can look at this as being both zeros, this as being ones, and you can look at this as x. All right, so that's the truth table, A, B, the result of OR, the result of AND. So if you treat this as a constant, 0 or 1, and you treat this as x, let's look at this. X ORed with 0, so I'm going to look at the place where A is 0, and B is x. So if you put in a 0, you'll get out a 0. If you put in a 1, you get out a 1. It's almost as if ORing with 0 doesn't change anything. And that's exactly what this identity says. X ORed with 0 is just x. That's called the identity property. And there's a corollary for AND. X ANDed with 1 equals, and we can look at it. So if we examine where A is 1, let's look at what happens when we AND things. If you put in a 0, you get out a 0. And if you put in a 1, you get out a 1. So it's the same. If you AND something with a 1, you get out whatever you started with. If you OR something with a 0, you get out whatever you started with. So that's our first property. If you have an operator, AND or OR, you might not need it at all if whatever's on the other side of this equates to 0 or 1, true or false. We can also switch that around. X ORed with 1 and X ANDed with 0. So let's again look at the truth table. When you OR something with a 1, so if you put in a 0, you get out a 1. If you put in a 1, you get out a 1. So the truth is, it doesn't matter what you put in. If you OR something with a 1, you will always get a 1. And if you AND something with a 0, doesn't matter what B is or what X is, you will always get a 0. And this is called the null theorem. The idea here is, depending on if you're ORing, so if you OR with a 0, nothing changes. If you OR with a 1, it doesn't matter what X is irrelevant. It's going to be 1. So ORing something with true means it doesn't matter. You can think of this also like in multiplication. It doesn't matter how long or complicated an equation is in regular algebra. If you multiply by 0 somewhere in there, it all turns to 0. Okay. And actually, the AND follows the multiplication theorem pretty well. If you multiply something by 1, you just get that something. All right, so those are sort of the basics. We can go on to a few other things. X ORed with X, and X ANDed with X. All right, in both cases, it's just X. So X ORed with X is going to be X. x ANDed with x is going to be x. And this is the idempotence. Idempotence theorem. The idea is if you're ORing something together with itself, it doesn't change it. Again, it's removing an operator. The other piece of this is if you x or x bar, x AND with x bar. Okay. So look at it this way. If you have a 0 for x, 0 or x bar, 0 or 0 bar is 0 or 1, which means you'll be in this row right here. 0 or 1 is a 1. And if x is a 1, you'll have 1 or 0, which is also a 1. So if you're looking at something or its opposite, it's always going to be true. Again, we have eliminated x from our equation. Now this, it's the opposite. If you're trying to see if you can get something and its opposite at the same time, you will never have that. As a result, that is 0. And that's the complement theory or complementarity. All right. This next one, it doesn't really apply to and or. It's kind of its own thing. So let me just sort of show that there. If you take x and you invert it, and then you invert that again, you end up back where you started. All right. I don't have the not table up there, but that makes sense, right? If you take a 0 and you invert it once, 0 inverted is a 1. If you invert 1 again, you go back to 0. Okay. This is just involution. If you negate something twice, you end up back where you were. All right. Moving on from here, we move on to things with 2 variables. So I don't need that anymore. 2 variables, such as x or y. Well, x or y is equal to y or x, and x and y is equal to y and x. Now, this might seem like a duh kind of a thing to you, okay, but it is important that we have this. This is something you should have been seeing in regular algebra. This is commutative, the commutative property. 2 m's, okay, commutativity. And also, if we have nothing but ors, for example, x or y or z, it doesn't matter what order we do it in. We can do y or z, then or that with x, or we can do x or y, and then or that with z. And the same with ands. X, y, z, x, y, z. We can put the parentheses in any order we want, and that's associativity. These should be more familiar to you. All right. Now, this last one can give people a bit of a problem. Everybody, I think, is going to be pretty okay with the idea that x ANDed with y or z, in parentheses, is equal to xy or xz. That should look familiar. You can multiply out. Okay. This, by the way, is distributivity, the distributive property. Where people begin to have a problem is with the converse of this. X or yz is equal to x or y ANDed with X or Z. It is doing exactly the same thing as the OR case. You're taking and you're applying that OR symbol to both variables and connecting them with the AND. It's exactly what we did over here. We took this AND, it became X and Y, or, I should have this open, X or Y, ANDed with X or Z. Here, we're distributing through ANDs, which you're allowed to do in Boolean algebra. All right? All right. Now, I should say that X doesn't just have to be a single variable. X can be any expression. It can be a very long and complicated expression, and that's allowed. If you have any long, complicated expression ORed with 0, at the end of the day, it's still just X. If you have a long and complicated expression, all ORed with 1, it's 1. That complicated expression goes away. So these are definitions. We're starting here. Any questions there? All right. There are one more set, okay, of laws that we work with, right? And we'll go through those now. Absorption. Okay, the absorption property says that if you have X or X, Y, that's the same as X. That might seem a bit counterintuitive to you. How can you just get rid of Y? Well, consider for a moment the truth table for that, because most of these can be proven pretty simply just by drawing out the truth table. Okay, if we look at X, well, that's just copying directly from that column there. If we look at X and Y, it's going to be true only where both of them are true. Excuse me, oops, undo. Only where both of them are true, X and Y. If we look at the combination, the OR combination of that and that, any place that either of them is a 1, we're going to have a 1. So you can see that the fact that this 0 is here doesn't matter. The OR quantity is just X. And that's one way of proving these theorems. You just show a truth table, go through all the possible combinations, and it's pretty clear that what you end up with is what you started with. Y doesn't affect this. So the book goes through this a little bit. I'm not going to belabor the point. We're just going to use them. Okay, so also there is a corollary to this. X ANDed with X or Y is also X. All right. As we continue on, look at this guy. X, Y, or X, Y bar. That's also equal to X. This proof, I think, is a little bit easier to see just using algebra. So if I take X, Y, or X, Y bar, it's pretty easy to see that X is in common to both these terms, and I can factor out Y or Y bar. I've effectively used the distributive property, right? X or Y, X and Y or X and Z, X and Y or Z. So in this case, this was Y and this was Z, all right? But I can use yet another property to reduce this down. Y or Y bar is the complement property. Y or Y bar is always 1. So now I have X and 1. Final property, the identity property. X ANDed with 1 is just X. Okay, so proof by algebra is also possible here. Get rid of that stuff. Okay, the complement, or not the complement, but the reverse of that x or y ANDed with x or y bar is just x. Minimization property. The idea that if a variable doesn't matter, doesn't affect the equation, we can just get rid of it. Okay. Let's see. Oh, we've also got x or x bar y is equal to x or y. And its corollary, x ANDed with x bar or y is just equal to x, y. That's simplification. Okay. The idea here is it doesn't matter that you have this x bar here, because if it's x bar, then y obviously has to be true because it doesn't fulfill this term. If you look at when x is 0 and x is 1, if x is 1, it's automatically true. If x is 0, then it's reliant on this term, so the x bar doesn't enter into it. Okay, next one is a little bit longer. xy or x bar z or yz is equal to xy or x bar z. I'm not going to go over proving that one. It's the one I find least useful. X or y, x bar or z, y or z is equal to x or y, x bar or z. This is called consensus. All right. The book actually does a really good job proving this, I believe. But it's really just using these other properties to get to that. All right, the most important one. If you forget everything else in this course, you should remember this law. It is my favorite law, which I apparently can't spell. It is De Morgan's law, named after a guy, De Morgan. It says that if you have x or y, and you invert the whole thing, that is the same as taking each term, inverting it, and ANDing it together. So here's where I need to be really clear. Okay, I'll write down the corollary as well. X and y is equal to x bar or y bar. X and y inverted is not the same as x inverted and y inverted. They are very different. So you can't just be willy-nilly about your overbars. There is a definite separation here. Now, the trick to remembering De Morgan's law is split the line and change the sign. If you can remember that little mnemonic, you will be fine. Anytime you see an OR symbol or an AND symbol, doesn't matter, and there's an overbar over both terms, you can split that line right in half, and you'll end up with x bar, y bar on either side, and you change the operator from OR to AND or from AND. Oh, you can't see my pointer, can you? From OR to AND or AND to OR. In both cases, you go from a long line to two short lines, split the line, change the sign. I know that I'm running a little late. I want to give you some homework. Don't go anywhere. Okay, where are we? Chapter 2. Come on. Okay, homework from chapter 2. One through 7, 9, and 11 through 14. I'm sorry, hang on. Nope. Just to 11. Actually, just forget those. Just forget 11 to 14. 1 through 7 and 9. They ask you to simplify using these properties. All right. We have lab this afternoon, right? Okay. As a reminder, I expect you to all have, at a bare minimum, a schematic drawing and breadboard of what you're going to do for however many sections you're going to perform today. I would guess, for the most part, that most of you are not going to make it past propagation delay. It just takes a while to do these pieces. So as a bare minimum, you need to submit to me pieces of paper with your name on it, schematic, and breadboard layout, which means you need to print out a copy for yourself. I need 1 per group. Okay? So you should already be set up in groups of 2, 1 per group. All right, I will see you this afternoon.